Hello, this is the alternative delivery for Math 2115. First thing I'd like to do is maybe give you a more simple answer than what I gave in one of the solutions to the last one. The question that was posed was, if you have an equivalence relationship and you want to know everything that is in the equivalence class of a given element x, and you have a relation on x and x that is an equivalent relation, what's the easy way to do it? And you see, I could just say without loss of generality, x is here. And so if x is here, then what would happen is the equivalence relationship then would either be, and this is a much simpler answer than I gave, it would be the row where it's showing everything that is equivalent to x. So it's the row containing x. Or, likewise, since it's x is the first column, it could have been the column containing that. And I was trying to do something fancy to isolate these, but you really just can read them directly from the matrix. So that's a much simpler answer, and that's a good answer. And I was going to say that, oh, and this thing is an example of an equivalence relationship where I could do that. Except, as I was glancing at this again, I decided I would check to see if, in fact, this was transitive. Clearly, by inspection, it is symmetric. But when I multiplied these elements by themselves, you see that I start getting non-zero elements down here, so this is not transitive. So my answer that I said at the beginning was a good answer and corrects the complicated things that I said before, but this is a bad example because this is not an equivalence relationship because it's not transitive as seen down here. We're finished with chapter 3.5, and we're going to be skipping chapter 3.6 for now. But I do want to say that if you know about relational databases and can program in a structured query language, you can get jobs at COD working in institutional research or many places dealing with relational databases. These programs run from very sophisticated Oracle programs doing SQL to low-level sort of desktop things like Access that do generate reports. And this is actually a big need in industry, and you certainly can get jobs doing these kind of things with relational databases. Okay, so we're going to be wading into this next chapter now. And what we're going to see is that this is going to be, I am going to cover the introduction briefly today about algorithms. And we're going to do some examples in this section. We're going to do more examples in this section, but I'm going to start talking about some of the mathematical underpinnings that we use in analysis of algorithms, and that comes back to some real math. And so we'll start talking about, we'll certainly do this, and we'll do a little bit of this today, and I'm going to be watching the time and seeing how far I actually can get. Okay, so what is an algorithm? Well, algorithm is a step-by-step method of solving a problem. And the word algorithm comes from a Persian mathematician his name was that, and that looks something like algorithm if you think about it. Anyway, this is typically refers to a solution that can be executed by a computer, and we'll be concerned primarily with algorithms that can be executed by a traditional computer, and that is that it doesn't require things where there are parallel steps. There will be instructions that are being executed step by step. Algorithms tend to have the following characteristics. There is input, there is output. The steps are precisely stated, and in fact sometimes you have comments that will describe those. The immediate results of each step are unique and determined only by the inputs and the results of the previous steps. So it is deterministic, it's not probabilistic. You can do simulations, things like that, but that is not what we're talking about when we're talking about an algorithm. An algorithm does end So it is finite. So it terminates after finitely many instructions have been executed. Often you have a stopping rule that forces this to happen. The output produced by the algorithm is correct. It's not a good algorithm if it's not correct. It does solve the problem, and demonstrating it solves a problem can be a mathematical proof. In the real world, what people do is they test the heck out of large software, and the algorithm applies to a set of inputs that are general in nature. Here's an algorithm that will find the maximum of 3 numbers, and this is written in pseudocode. So the input's going to be A, B, C. The output is going to be the largest of A, B, and C, and we're going to call it large. And so what happens is, this is the name of the program. You set A, the first element of the 3 numbers that you submit, to large. So you assign large the value of A. Then you go to the next one, and if B is bigger than large, then you assign the value of B to large. Then you go to the next if statement. If C is greater than large, and this is if C is greater than large, update large, you assign C. And so when you return large, you give us the biggest value. Now this can be proven via trace, taking examples, or more generally, as I said, a suite of text vectors. A suite of text vectors, however, does not really prove something unless it's an exhaustive suite, which in a complicated situation is often difficult to come by. We can look at generalizing this algorithm to say we want to find the maximum value in a sequence of numbers, where this goes S1 through Sn. So the input is the sequence and how big it is, and then you write an iterative do loop. And so what happens is, this is the name of the program, and so you take S1 and you set that equal to large, and then you do what we often call a do loop. We go from I equal 2 to I equal n, and we check each time if the next entry in the sequence is bigger than the large we have established. If so, we assign that large, and we go through this until we've checked everything and we've returned large. Now, since this is a general n, we actually are doing proof by induction on n, just like we talked about. And so that's a little bit involved, and you may want to think about how would you do that. But we showed that it worked for 3, and then if it works for n, we'd have to show it works for n plus 1 in the sequence. Now, I'm going to change gears just a little bit now, since we've talked about a couple of examples of algorithms and how you prove them. I want to talk a little bit now about some of the analysis. And we have to really think about math a little bit, and maybe going all the way back to the Cartesian plane, because we're going to be talking about functions in the xy plane. And this goes all the way back to Descartes, who in theory saw a spider drawing, or not drawing, but making cobwebs in the corner of his bedroom. And he started thinking about generalizing that to have a coordinate system. This was kind of a big deal. Descartes was quite a philosopher, and one thing he said was the first precept was never to accept a thing as true until he knew it was such without a single doubt. He started worrying about, does he actually exist? And he concluded that the only way he knew he exists is because he could think. And this is where the I think, therefore I am, or in Latin, cognito ergo sum, came from. But anyway, we're going to be talking a little bit about math. So we're going to be talking about functions, because we're going to be comparing the efficiency of algorithms to mathematical functions. So what we're going to do is we're going to let a be any non-negative real number, and we'll define p sub a to be the power function with exponent a. So p sub a of x is x to the a for each non-negative real number x. So this is one of the things that we will compare some of our algorithms to. And here you can see what the graphs look like. So this is y equal x squared, that's y equal x, that's y equal the square root of x, and that's the flat one, y equal 1. It doesn't really look flat on my chart, but that is a flat function. And what we're really going to be looking at, since we have algorithms that this is discrete math, so we're talking about non-negative integers in 1, 2, 3, we're going to be talking about growth like this, but we can certainly compare the growth that we're seeing here with the growth over here. So we are going to take our discrete values and compare them to real functions, and that's where we're going to be making a lot of the comparisons that we're going to be doing. Okay, so we can talk about a graph of a function defined on a set of integers, and in other words, and this is a problem I'm guessing I asked you to do, think about what does the graph of g of n equal n to the 1/2 look like, and sketch the graph. Now this is one of those things where you probably should pause and kind of sketch this out and then return for the solution. Well, here's the solution. So if you draw the graph, what would happen here? So 1 is 1. This is going to be 1.4. That is going to be 1.7 and change. You're going to go to 2 here. You have to go all the way out to 9 to get to 3, and so on and so forth. And at 16, we would be up to 4. But you see, this is what it looks like. And you see, if you were connecting the dots, you would say this is growing as the square root of x, or the square root of n. Okay, now we can talk about the multiple of a function, and the multiple of a function, and here's just a definition about that, is so we talk about f being a real valued function and m is a real number. Then if it's a multiple, what happens is m times f of x is actually just m times f of x for each x in the development in the domain of this. And so you should be able to understand what this multiple thing means, and let's look at an example of it. So here's a function whose graph is shown below. I'm going to ask you to sketch a graph of 2f, and so pick some points and sketch this graph before you continue, please. Okay, here's a solution. So at each real number x, you obtain the height of the graph of 2f by measuring the height of the graph at x and multiplying that number by 2. And so here you can see that that happened in each case. Now in some case, we went from what was previously 1 to being 2. Some things didn't change though, and the places where it is 0, of course, don't change, because 2 times 0 is 0. We will be concerned about whether things are increasing or decreasing. And so we say if f is a real valued function, it's increasing on a set S if whenever x1 is less than x2, f of x1 is less than x2. Another way to think about this is if the x's get bigger, the y's get bigger. Similarly, it is decreasing on S if when x gets bigger, the y's get smaller. And so, and we can talk about things that are strictly increasing or strictly decreasing if it's increasing or decreasing over its entire domain. Now, if something is truly a strictly increasing function or a strictly decreasing function, it has to be one-to-one because it's getting bigger all the time. So if f of x1 equals f of x2, x1 has to equal x2. And in fact, that's a proof that you should be able to do. It does follow almost immediately from the definitions. Okay, and here is something that it is a proof. It is not a difficult proof, but I'll ask you to pause and give this a try. Positive multiple of an increasing function is increasing. Okay, so suppose f is a real valued function, and m is any positive real number. Show that mf is increasing on S. So pause, give it a go, and return. Okay, here's the proof. So suppose x1 and x2 are chosen such that x1 is less than x2. So we must show that this is true. So that means that f of x1 is bigger than f of x2 because it is increasing. But then m, when we multiply by a positive number, the sense of the inequality is preserved. So m of f of x1 is less than m of f of x2. And so by the definition, we know that this one is less than this one, and consequently, since this was arbitrary, it is an increasing function. Now, we're going to start talking about big O, little big omega, and Big-Theta notations. But actually, I do want to go into a little bit of math history with this because um, it is, I think, quite relevant. And Babbage is thought to be one of the inventors of the computer, and you can see that he was like 100 years before computers were really there. But what he said is, as soon as an analytical engine exists, it will guide the future course of science. That is really true. Whatever result is sought by its aid, the question will then arise, what course of calculation can achieve these by in the shortest time? And that is what we're really talking about. We're talking about estimates as to how efficient are algorithms, and we're going to be using notation that is of this form. So understanding the efficiencies of algorithms is much more than academic interest. In industrial and scientific settings, the choice of efficient over inefficient can save a lot of time and money, and in fact can be the difference between being able to do a project or not doing it at all. So in this chapter, one of the things we'll be doing is taking algorithms and trying to see which algorithm can do it most efficiently, and estimate between the best case and the worst case of the algorithm performing the task. And in fact, here is an example of the worst case to best time for processing an array. This is an assert. Here is a scheme that's called range for insertion sort, and you see that the range for an insertion sort happens. You will go from this value to this value, whereas the range for a merge sort, which is much more efficient, will go from best case to worst case in this range. So you can see, and especially as the number gets larger or as x gets larger, this is definitely the way you want to do it, and this algorithm should not really done at all except for maybe very small problems. Now, we're going to talk a little bit about this guy. He is a genius of the first order. And I'll say more about him. Here in the Math Encyclopedia, they say he's an American mathematician. Other people would say he's a computer scientist. I think he's actually a professor of computer science now, who's most famous for inventing a typesetting language. Actually, he invented this typesetting language because he wrote a 3,000-page book and was really depressed about how long it took to typeset it, so he invented a separate typesetting language. He received a bachelor's degree and master's degree simultaneously, and during summer vacations he was writing compilers for, I think it was IBM, and making way more money than his professors did at their full-time job. A really incredible guy, and he's from the Midwest. I think he was born in Milwaukee. Here are some things that he has said and others have said about him. Here he's saying that he has a great name for a programming language, but he's now looking for a suitable language. He says science is what we understand well enough to explain to a computer. All the rest is art. Kernighan, who was one of the co-inventors of the C programming language at Bell Labs, quoted Knuth in his book about Unix programming environment. Bill Gates said, if you think you're a really good programmer, read his book, which is called The Art of Computer Programming. You should definitely send me a resume if you read the whole thing. It's quite an opus, and I encourage you to maybe check it out in a library or something like that. He is a very complicated guy, and some of the exercises in his book on discrete math are research problems, and in fact he's sort of quoting somebody else, but he really was talking about himself, I think. What's the difference between a research problem and a exercise? So if you can solve it, it's an exercise, otherwise it's a research problem. Now, the reason I talked a little bit about him is that we're going to generalize the notation that we talk about in our book just a little bit. So the symbols capital theta and capital omega are upper Greek letters theta and omega, and this determines ranges of things, and we'll talk more about this. Now, these are related to older notation that is called the Big O notation, that was introduced in a book on number theory and was first to be used to compare the efficiency of algorithms. But later, in fact, we'll look at examples where the Big O notation alone can produce ambiguous or even misleading results. So he realized the shortcoming, and in fact here they're talking, he was a pioneer in the analysis of algorithms. He introduced this new notation so the functions could be compared with greater precision. Okay, so here is kind of the quick version of this. If for sufficiently large values of n, the values of f are greater than those of a positive multiple of g, then is of order at least g, and you write omega g of n. If the values are positive and less than that, we say f is of order at most g, and we use big O. If for sufficiently large values of n, the values of theta are bounded above and below by positive multiples of g, then f is of order g, and when he says order here, it's not big O or little o, it's order, and this is going to be the O that is called a theta, and I will tie this to the notes in your book as we go forward. And here are some graphs that you may want to pause and realize that this is talking about the growth of these functions as n gets large. And so here's an example of being omega g of n, here's big O of g of n, and here's being theta, or the order of g of n, caught in between the two. Okay, and this really talks about the fact that even though we're talking about real valued functions, we're really in discrete math concerned about just integer n's, and so we're really going to be restricting ourselves to these discrete values when we're writing, although we're going to use the other notation. So here is a definition. You probably want to pause here, but this is the definition rewritten. Instead of using x's, we're using n's, and so this shows what happens if f of n is omega of g of n, or big omega, I guess we can say, because that's capital. This is big O g of n, and this is big theta of g of n. And let's do just a couple of examples, and I think I'm about ready to pause this for the day. But everybody pause and give this a show. Think about what is going to be the theta notation here for this. So use theta notation to express this statement. So pause and I'll come back with an answer. And here's the answer. Since we can have, if A is 4 and B is 30 and K is 3, so for n bigger than 3, we know that this is between that, and we will say that this is theta of n to the 6th. That means this grows like n to the 6th because it's bounded by 2 multiples of n to the 6th. Here are some other examples, and this does involve the floor functions. So let's talk about translating to these two notations for A and B, and then deduce the theta notation that's shown in C. So I'm going to pause, ask you to read this, think about it, and then we will talk about solutions. Okay, let's talk about solutions now. Okay, so we can find that since if A is 11 over 4, capital A is 11 over 4, and lowercase a is 2, the statement translates to this for every n bigger than A. So what we can say is that since this is bigger than A, that this is going to be, we have 3, and this is less than n squared, that is less than n squared, so the sum of this is going to be omega of n squared. Similarly on B, what we can have when B is 6 and lowercase b is 1, we can say that this is true, And since this is less than n squared, this is b of n squared for every integer n bigger than or equal to b. So by the definition of the big O notation, this is big O of n squared. Note that for this problem, omega n squared is the same as, well, we're talking about big O here, but you see both of these are bounded by the order of n squared. That is, they grow less than a multiple of n squared. But what we can do is we can combine the two, and since we know that this expression is between an squared and bn squared for every integer k, where k is the larger of the two, then by the definition of the theta notation, this is big theta of n squared. Now, I'm going